All right, so our next speaker is Victorial Walker from Embry Riddle Aeronautical University, and she's going to be talking about modeling soil moisture from rainfall at network sites. Just up and down here.
Up and down there?
Oh, back. Different systems.
Okay. So Victoria Walker, I'm an assistant professor at Embry Aeronautical University, the smaller campus in Prescott, so the desert campus, not the Florida one. The QR code that's on here goes to a paper that came out in March, I think, in Beto Stone Journal. This is done with work while I was still an ORISE postdoc hosted by Mike at the USDA ARS. And then Todd, Ronnie, and Kent Sutcliffe were also on this paper. The arrows are not making it work.
What it is it's just clicked away. So if that happens, click back. Oops. Click back here and it should. I tested it a minute ago.
Use the arrows?
Okay, yep, just use those.
All right, so we're gonna talk about the diagnostic soil moisture equation. This originally was developed in 2012. You take antecedent precipitation, so you have to decide how long a window you're going to look at. For this study, we looked at 30 days, but the original formulation used 90 days. And then you do a station-specific loss coefficient. So you're taking co-located soil moisture and precip information and saying how does my soil moisture decrease with time after rainfall? So it's going to be related to drainage and evapotranspiration. It was originally a daily formulation. We've turned it into an hourly. There was a paper in 2015 that validated it over a bunch of SCAN and USCRN sites, but with a limited data record. So what we've done now is gone over a larger record. We've got an additional decade of data, more stations, and we looked at some specific questions. The big one was, how much data do you need in order to calibrate this model? So how long of a co-located record do you need before you can start going back and simulating historical soil moisture for that site? Are there circumstances that impact that model's performance? Some sites it just doesn't work very well at. What are those circumstances, and what are some things you can do with this? There it goes. So I do want to say a note on rainfall data first. Since rainfall data is your big input on this, you want to be really clear on the quality of that rainfall data you're putting in. So if you have a gap in the rainfall, that's going to cause a larger gap in your simulated soil moisture. Because if you're looking at a 30-day window and one of those was a NAN, you'll then get a NAN for your simulated soil moisture for the next 30 days while that's in your record. If your rain gauge is reporting all zeros and not tipping, even though you know there's rain events, that will get you a simulated soil moisture at the bottom level. If your rain gauge is reporting a whole lot of tips, that's going to give you a simulated soil moisture that's very, very high. And then you'll see your simulated soil moisture does not match up with your actual in terms of temporal dynamics because that rain gauge was doing something funny. So how much data do you need to calibrate this model? You need a minimum of 2 years. The goal is to include both wet and dry extremes. We want to capture the whole range of soil moisture conditions. If you have more than 2 years of data, go ahead and use more of that data in your calibration. We tested all possible combinations of 1 to 5 years and came up with, of the sites where it would achieve an acceptable calibration eventually, it took a minimum of 2 years to reach that across the network. So I looked at all the CRN sites except for one that was too high of a salinity. It was doing some weird things. And then the scan sites, those got filtered down by visually going through all the time series and saying, is there anything weird in this? Like, is there an anomalously high amount of precip tips at this site? Or is there like random spikes in soil moisture that we know it's not something real? So we're going to go, where does it work best? So this is all of the sites that we tested it at that had the data available for a calibration based on just the initial 4 years. So where there's an X on this map, that's a site that was part of our testing for calibration length, but it didn't have that first 4 years of data, didn't meet a certain availability criteria to get onto this map. I'm going to see here, there's certain places that just don't calibrate well. About a quarter of the sites on this map, the RMSE wasn't able to get below 0.06. That means about 3/4 of them it did. Of those sites where it was not able to get below 0.06 with 4 years of data, about half of those, when I went in later, you could find more data quality issues that just hadn't been widespread enough for me to flag them on the first time through. But more of those like spikes in soil moisture, but maybe it only happened for a few months, so I didn't discard that station right away. Other things, if the calibration period does not match your validation period, so let's say the years you used for calibration were really, really dry, your simulated soil moisture is not going to get as wet as it should during its validation period. If snow melt is an important process for you, this model does not capture snow melt. Also irrigation, horizontal, like subsurface flow, those are all things that are too complex to be part of this diagnostic soil moisture equation, so it throws off this error. But there's some sites that we also just don't know why it didn't quite work. Some of that is going to be clay fraction. So there is a relationship of validation RMSE to clay fraction. So out of the CRN stations that were on that map, about 60 of them had reported soil textures at the 5 centimeter depth. So everything I'm showing today is at the 5 centimeter depth. This model can be run for different depths, but you'll note it's not like the 10 centimeter would not be this at 10 centimeter, it would be the 0 to 10 centimeter. Validation RMSE increases as clay content increases. The more clay your soil has, the harder time the model has at matching what the sensor measured. What about the extremes? It does really well in the middle of the distribution. As you start tailing off into those wettest and driest of events, it's like the top, the driest 10%, the wettest 10% of your measurements, that's where the error starts to get larger, especially with the hourly performance of the model. So if you chose to run this on a daily time step, you might not see as many of those extremes right after rainfall, because I did not exclude right after rainfall measurements from this. I did exclude frozen soil or soil below 2 degrees Celsius, but not after rainfall. I left the rainfall data in. So we just can't get quite as extremely wet or dry as the in situ does, but for the majority of the range, we're doing pretty good here. This is for a CRN site in northwestern Kansas, and it's the same one that we're going to see right here. So this is a simulated record. Where on the top, you have the in situ soil moisture. In the middle is the precip, and on the bottom is the simulated soil moisture out of the model, where we've taken the first few years of the data, calibrated this model, and said how much, what do we think the sensor would have seen over that period beforehand. So remember, consider gap filling your rainfall first if that's an issue, because if you don't, you get gaps in your simulated soil moisture. And note how there's a calibrated max and min to that simulated soil moisture. So it just doesn't, again, those very, very, very wettest, very, very driest, we just don't see those because of how the model works. The other thing you can do at this is you can check for sensor abnormalities. So this is a scan site that has about the same overall error as that CRN site did. This one's in North Texas. This is monthly RMSE compared to precip. In the bubble that's circled number 1, that is the soil moisture was fluctuating, but there was very little rainfall observed. So one of those 2 sensors probably needed attention. Something was off there. It ended up being that they replaced the soil moisture sensor. After they replaced the soil moisture sensor, we got to this bubble number 2 here. It has a different air dynamic that the model doesn't work quite as well for this new sensor as when it was calibrated for the old sensor. But the data set for this station is all just presented as one time series. And that note that a sensor was replaced is kind of tucked away in an additional metadata form. So there's a question here of, can we be combining these two without a data flag? They have different air metrics. Are they seeing different things? So our key takeaway here, you can run the DSME. It's just a Python code, command line, let it run in the background. You need a minimum of 2 years of co-located soil moisture and rainfall data to do this. Something that's really obvious, but I'm going to say it again, is that your input data quality significantly impacts your output. How reliable is your simulated soil moisture coming out? It's going to depend on your calibration data, that co-located record, but also just the entire rainfall record you're using to simulate it. That if there's issues with that rainfall, you're going to see issues with your simulated soil moisture. And then just a side note here, all the RMSEs were the difference between the simulated soil moisture and the installed sensor. That installed sensor has its own air, so that's not being compared to like a ground truth, a gravimetric sample. It's just the model compared to the sensor. If you'd like more information about the model or the Python code that runs it, feel free to send me an email. This is the same QR code that was there at the beginning that links back to that Vadosone journal paper.
All right, so we got, just like last time, we got time for one question as Lee sets things up. If we got one in the room. Peter.
Yeah, so this is really interesting. You said near the beginning that you're using just precipitation and a loss function to derive your soil moisture, right?
So it is okay. So the question was the function is driven, it's antecedent precipitation, and then there's a fitted loss coefficient. The function itself is like a summation over your antecedent window where like what happened yesterday has a lot more weight than what happened. Evapotranspiration is in there as a theoretical, it's got like a sine wave function for day of year.
Okay.
So day of year is a component of that input function. But the pieces of data that you need are the antecedent precip and then that co-located soil moisture and precip to do the calibration on.
Okay,